Welcome to ECE 302. This is lecture 5.9 on high-dimensional Gaussians. I'm Professor Stanley. In the last lecture, we talked about random vectors. It is a high-dimensional extension of the joint distributions that we have been studying so far. A random vector is denoted as a vector of random variables. Here I have random variables x1 through xn. Each of them is a random variable. This notation with a bold letter X, it denotes the vectorized version of all these random variables. It is a random vector, meaning that it has its own probability distribution. The states that this random variable, this random vector x that takes is denoted by this small x. It is another vector. And this vector, it also has n elements, which is the same dimension as the random vector. So we can ask, what is the probability distribution for this random vector? And it is denoted by this symbol, where you have a random vector x, and you're asking about the probability distribution. What is the probability of getting this particular state, which is a vector? Now, in the continuous case, you define the probability density function in high-dimensional space, and therefore, when you integrate the high-dimensional PDF, you'll be able to obtain the probability. Given the PDF, this is a joint PDF, it is a high-dimensional PDF, we can also define the mean vector, which is essentially just taking the mean of the individual elements of this vector. Furthermore, we can define the notion of covariance. The covariance is defined as this matrix, depending on how many elements that you have in this random vector x. You can define an n by n matrix where each entry denotes the covariance. So it is the covariance between xi and xj, where xi would be the ith element of your random vector, and xj would be another element of your random vector. Of course, if you're looking at xi and xi, for example, here you're looking at x1, then the covariance of x1 and x1 will give you back the variance of x1. And therefore, you can see that in this covariance matrix, along the diagonal, I have the variance of the individual elements. And then this covariance of the other pairs of random variables, they can be 0 or they can be non-zero, depending on how much correlation that you have. In the particular case, where x1 and x2 or xi and xj in general, they're independent, then you can show that all these covariance terms, they will go to 0. In that case, you will only have this diagonal matrix. So this is the notion of random vectors. It is something that we learned in the previous lecture. Towards the end of the previous lecture, we also introduced this idea of multidimensional Gaussian. A multidimensional Gaussian is really characterized by this joint Gaussian PDF. It is a high-dimensional PDF taken this form. In this expression, we have this quadratic equation here. You have x and then mu. Mu is your mean vector. Okay, so and then here you have x and mu again, and in the middle you have a covariance matrix, but now you take the inverse. And we know that why there's an inverse here, because the covariance matrix defines the variance. Think about the independent case. Now if you take the inverse, then you will have all these reciprocal of the variance. That's why you have this inverse here, because you want to take the reciprocal. Now, how about the dimension of this term? We know that this x and mu, they are column vectors. And then this matrix, of course, it has to be a square matrix. And then on the left-hand side, you have this vector, but then you take the transpose. And so you're taking this row vector times a matrix times a column vector. That would give you a scalar. That's a number. So plug that number in, and then you take this exponential. That will just give you another number. And then in front of this expression, you have this normalization constant, where d defines the dimension of your random vector x. So if your random vector x has d elements, then the d will come out here. And then this term is the determinant, the determinant of this covariance matrix sigma. Now, this is a high-dimensional extension of the 1D Gaussian that we have learned in the previous chapter. This is not too much different as soon as you can recognize this quadratic form and also this constant. So what we want to do today is to understand more about this multidimensional Gaussian. A few things that we want to study. Number one, we want to know what will happen if all these random elements of the vector, they are independent. Are we able to obtain something much simpler? And if yes, what will they look like? The second question that we want to know is, on computer, this is a very practical question. On computer, how would you ever draw samples from this high-dimensional Gaussian, and how do you visualize them on a computer? What kind of programming languages, what kind of commands that we need to use in order to show a Gaussian distribution in high-dimensional space? The third question that we want to ask in this lecture would be, can you describe the shape of the Gaussian? If I provide you the mean, if I provide you the covariance matrix, would you be able to tell me the orientation of this Gaussian? So we are going to look at these three problems in this lecture. To start with, let me talk about the independence. So assume that all these random elements, x1 through xn, they are all independent. Then what will happen to your covariance matrix? As I said, if all the elements, they are independent, then this matrix sigma will become this. Now notice that all these terms, these cross terms, the covariance terms, they all become 0. That's because if xi and xj are independent, then you can show that the covariance of xi and xj, which is the expectation of xi and xj minus mu I minus mu j, and since they're independent, this will just give you mu I times mu j. And so these two terms will cancel out, and so you will have 0. That's why if they're independent, then all the covariance terms will go to 0. Now, if this happens, then we can ask, what will happen to your quadratic term? This is the term that you plug into the exponential. So you write x1 minus mu1 all the way through xd minus mu d, and then here you take the transpose, and then we put the covariance matrix into this inversion, and so you keep this inversion here. Now what happens when you put an inversion? Well, this inversion will be gone, and then you have 1 over and 1 over here. Then you start to do this calculation. You start to multiply this matrix with that vector, and you can have this x1 minus mu1 divided by the sigma 1 square. So all the sigmas, they go to the denominator of this this vector. And then you take the transpose again. What will it become? It will become the summation of all these individual terms. The individual terms, you will have xi minus mu I, and then you have sigma I square in the denominator. And therefore, this quadratic equation can be written as the sum of individual quadratic terms. Now, you are not able to write this thing very easily when you have all these covariance terms, because in the presence of all these other covariance terms, you will have xi minus mu I, and then you have xj minus mu j. So you won't have this square very easily. You will have this cross terms, and they're floating around. So you also have x sigma I and sigma j. So all these, they are here and there, and then that will cause a lot of problems to your calculation. And so so this is a nice thing about the independence. Independence says that if all the random elements of the vector, they are independent, the quadratic term can just be written as the sum of the individual terms. So if you plug that in, you can show that the PDF, the joint PDF of Gaussian, when everyone is independent, you just have this exponential to this quadratic term, and then you have this power. In this I going from 1 all the way to n, that stands for all the possible elements. And then what? And then you can show that. So this is not n. This is actually d. Okay. And so now what happens to this constant term? The constant term, of course, you need to take care of the determinant. The determinant of this diagonal matrix is just this product of the diagonal. So that will give you the diagonal terms, which is the product of all the sigma I square. And so when you plug that in, you have this product of the sigma I square that goes into this thing here. And then when you take the 1 over square root, you will have this constant. And therefore, the expression for this joint PDF or for the high dimensional Gaussian, as long as they're independent, it will be this very simple expression. So that's the nice thing about a Gaussian under independence. So how do we visualize the Gaussian random variables on a computer? I'm showing you an example here in MATLAB, and there exists a one-to-one correspondence between MATLAB and Python. And so I will encourage you to try this set of commands in Python. Just look up the internet and you will be able to see the corresponding commands. In this example, I am using this mean vector 0, 0, and then this is the covariance matrix. It's given by these 4 numbers. So this number stands for 0.25, and then 0.3, 0.3, and 1. So that is my covariance matrix. The way to draw the Gaussian random variables, which correspond to all these 1,000 crosses on this data point, is given by this command, multivariate normal. Okay, MVN, multivariate normal. RND stands for random number. And then you plug in the mu, you plug in the sigma, you plug in the number of samples you want to draw. That will give you all these crosses. So what would they look like? So each x will be a 2 by 1 element. So that will give you each coordinate. So you have the x coordinate and you also have the y coordinate. And then you have 1,000 pairs of all these coordinates, and they can be marked on this figure. This set of commands tells you how do we actually plot the curve that I am showing you here. Now the visualization takes a little bit effort, and but you can sort of understand that this command is not too hard to digest. So given this 3 lines of code, what you'll be able to obtain will be the crosses. Now putting the crosses onto a figure is very easy. You just call this command of scatter. Okay, so this is the command that you can use to just plot all the crosses on the figure. So that will give you all the red crosses. Now on top of this, of course, you want to generate some kind of contour. The contour map will tell you the shape of this Gaussian. So how do you do that? Well, we know that on computer, drawing lines is actually done by drawing points and then let the computer do the interpolation for you. So that's the same thing on MATLAB. So first of all, you specify a grid. Okay, so this is the mesh grid command. It basically says that I want to have x-axis, y-axis, where I define a grid on all these intersection of the grids. I'm going to calculate some numbers. So that defines the grid. And then on this grid, I'm going to compute the probability density values. Okay, so I plug in this command, MVN-PDF. This is basically saying that I go to this point, I calculate what is the probability density for this mu and sigma. This is my Gaussian. Okay, so I plug in the number, and I see what would be the probability value over there. and then go to next point and go to next point. So basically, I will be able to calculate the probability values everywhere on this plot. It is a very dense plot. I have values, and once you obtain this value, you have this f. F is a very large array that contains how many rows and how many columns of numbers that you have computed on this for this grid. Then you reshape them. That basically you turn them into a long column vector so that they're indexed, and then you do this command contour. Okay, so contour basically says that all the numbers on this grid, they are the same value. I'm going to connect them. So that's a built-in command in MATLAB. There's a similar command in Python that would do this. Would do the same. And so you plug in x1, x2, which are the grid lines, and then you put in this f. F will be the values, and then you tell the computer what are the contour levels that you care about. Here I'm just giving you the levels of contour lines that I want to look at. So plot these. That will give you a contour map like this. Okay, so this is the visualization of a high-dimensional Gaussian, and I hope you can try this at home. Now, you realize that this is a Gaussian, and then it has certain orientation. It is an ellipse, that's for sure. It has certain orientation. In this example, is it has a major axis pointing up, and then you have a minor axis over here. So we ask, are we able to determine the orientation of this Gaussian? So that goes to the next topic, which is the eigenvalue and eigenvector decomposition of the covariance matrix. So the question we ask is, how do we determine the shape of a Gaussian? And the answer is by means of eigen decomposition. Now, I know some of you have already taken a linear algebra course on this topic, so you know what is the eigenvalue. But some of you may be not so familiar with this eigen decomposition. Let me just tell you what it means. The eigenvalue of a matrix, of a square matrix, is defined as this equation. So you have a matrix A, and then you plug in a vector U. Okay, so imagine that you have a box which is A. You plug in a U. What comes out from this A matrix is a U again. Okay, of course it may not be the exact same U. It will become a scaled version of the U. So think about a system. So this is a black box, and then you send some function. You send some sinusoid into this function. And then you look at the output. The output would be exactly the same sinusoid, but then you just multiply this thing by some constant. So this is what we call the eigen function. It is a very unique characteristic function that when you send it to this operator, it will come out itself. It will not be changed. So that's called the eigenvector. U is called the eigenvector, and lambda is called the eigenvalue. Square matrices, most of the square matrices, you will be able to obtain this eigenvalue and eigenvector. On computer, you can type a command EIG, for example, on MATLAB, to return you the eigenvalue and eigenvector. The eigenvalue and eigenvectors can also be obtained by solving equations like these. For example, you can solve a minus lambda I. You take the determinant of this matrix, you set it to 0, then the lambda will be the one that can set this equation to 0. A very fundamental theorem for this eigen decomposition is given as follows. If A is asymmetric, okay, then all the eigenvalues are real. Okay, so what do I mean by asymmetric? Asymmetric means that A equals to A transpose. Okay, so you flip the matrix over, you still get the same matrix, which is true for all the covariance matrices. In that case, all the eigenvalues, they are real, and then there exists a U, and then there exists also a lambda with this following property. This U is called the eigenvector matrix, and then this lambda, this big lambda, is called the eigenvalue matrix. You have this matrix A, which is a square matrix, and it is a symmetric matrix. It has all these columns, and then you can decompose this A into U times lambda times U transpose. This is a very special decomposition because when you decompose it in this way, the middle matrix is a diagonal matrix. A diagonal matrix is very good because the inverse is just the reciprocal of its diagonal elements. Furthermore, this matrix U has a property that U transpose U is identity. In other words, the U matrix is orthogonal. Not only that, all the columns will have a norm of 1. So if you give me a matrix A and I carry on the eigen decomposition, I will be able to obtain this decomposition form. On computer, you can just say that I want to obtain U and I want to obtain lambda, and then this is eigen of A. In MATLAB, this is the command. You just type EIG of the matrix A. MATLAB will return you a set of matrices. The first one would be your U, and then the second one would be a diagonal matrix, which would be your lambda. And you can do the calculation by yourself. You just multiply U lambda and U transpose again. You will be able to get back this A matrix. So this is a very useful decomposition of a matrix. So here is a example of how to do things in MATLAB. Basically, the command is this line, where you have a matrix, and then you run eigen decomposition, then you will be able to get U and S. S is the same as my lambda. Now, the command here is just to set up the problem because you need to type in some matrix A. This example, it just say that A is a 100 by 100 random matrix. I need to symmetrize it by taking the sum of its transpose divided by 2. Now, for otherwise, you won't be able to get the eigenvalue and eigenvector being real. Okay, so this is just to set up the problem, and then this small s is the diagonal elements of this matrix S. So S is a diagonal matrix, and then so this is big S, and then you squeeze out the diagonal of this S matrix. This is your small s. Okay, so this is the eigen decomposition in MATLAB, and you can do similar things on Python. So knowing the eigen decomposition, we ask, can we address the problem of the shape of a Gaussian? The answer is now yes, we can do it. If I give you the covariance matrix sigma, and then you run the eigen decomposition, then you will be able to obtain all these U, and then you will be able to obtain all these lambdas. It turns out that each column will represent a vector, and then here the first vector that corresponds to the largest lambda value, that would be your major axis, and then the second one will be the second axis, the third one will be the third axis. Of course, on paper and pencil, we can only draw up to 2D. If you have some imagination, you can go to 3D, but then going to a high dimensional space, we just cannot draw it. So here this diagram illustrates the case when we have 2 d equals to 2, you have 2 columns and then 2 lambdas. Now, the radius of this major axis, so here you have mu1, then this value lambda 1 will correspond to the radius of the major axis. Lambda 2 will correspond to the radius of the minor axis. And therefore, if I tell you the covariance matrix sigma, you run the eigen decomposition, then you will be able to determine the orientation and also the size of this ellipse. Now, you may ask, why is it always an ellipse? of course ellipse includes a circle, would it be possible to obtain something not an ellipse? The answer is no. You will always get a ellipse. This is because all the eigenvalues of a covariance matrix, they're always non-zero. Not only are non-zero, they're always are non-negative. The reason is that this sigma is a covariance, and it has the variance term, and so you have the square that is underlying, and therefore it is impossible to obtain lambdas being negative. And therefore, when all the lambdas are positive, you will have a positive radius. It's always positive radius. You may have a zero, but you will never get a negative radius, and therefore you will always get an ellipse. So here are a few examples. These are the examples that we have seen in the last lecture. We have a mean of 0, 2, 1, 2, and 0, 0. These are the covariance matrices, the first one, the second one, and the third one. What we want to do is to run the eigendecomposition and see if we are able to determine the orientation of this Gaussian. So let's try these three. Okay, so example 1, 2, and 3. If we run the eigendecomposition of this matrix, we will be able to get this u and this lambda. The u here is 0, 1. This one is 1, 0. So how do we understand it? This is the first column. Okay, and so this is the first eigenvalue. And then here is the second column. This is the second value. So now let's go back to the diagram. The first column says it is 0, 1. So that means you are looking at 0 along the x-axis. So you don't have any fluctuation in the x-axis, but then you have 1 in the y-axis, and so you have this. This is your vector. So let me draw it in green. So this is your the first column vector is 0, 1, 0, right? So this is a y-axis. This is pointing along the y-axis, and then the other vector is 1, 0. The other vector is 1, 0. Okay. Now let's also look at the radius. The radius is 5. So this is 5. And then here this is 0.5. Okay, so you can see that now this 5, of course, it corresponds to certain values of the standard deviation. There's a linear scale factor, but you can sort of see the ratio. This is 5, and therefore it is a lot higher than this number. Okay, and therefore you can expect to have more fluctuations along the horizontal line, and then you have less fluctuations along the vertical line. Let's try another example. This is your A matrix. You run the eigendecomposition, you obtain this u, and you obtain this lambda. The first column is given by these two numbers. The second column is given by these two numbers. And then here is the second eigenvalue. This is the first eigenvalue. So we ask, does it make sense? Well, let's look at the first column method. This is minus, so this is minus root 2. This is minus root 2. So what is it? Minus root 2 and minus root 2 is like this direction, right? Minus and minus. And then here you have minus and plus. Okay, so you have minus and plus, so you have this direction. And then you have this 0.5 and 1.5. So this is 0.5, and then this is 1.5, and you can see that it does match with the data because you have more fluctuation along this major axis. Okay, so let's move on to the third one. This is almost the same principle. So you have an A matrix here. This is your U. This is the first column of the U matrix. First column, and then the second column. And then this is the second eigenvalue, this is the first eigenvalue. And so you ask, what is the direction of this first vector? direction is minus and plus, and so it will be minus and plus, so it will be along this direction because it is going to the left hand side and going up. The other direction is plus plus, and so you have this direction. Then what are the eigenvalues? This is 3.9, this is 3.9, and the other one is 0.1. Okay, so you see that the direction really points to the right direction, and also the magnitude, they make sense. The ratio is 3.9 to 0.1. This is the ratio, and so you can see this is much bigger than here. This is 5 to 0.5, so this is 10 times difference, and then here is like a 39 times difference. And so we are expecting to see more dramatic skew in this diagram. So will you ever get negative eigenvalues? As I said, you will never get negative eigenvalues. The reason is that a covariance matrix is symmetric, positive, definite. It is a very special term that we use to describe the covariance matrix. What it means is that it is symmetric, and so the transpose equals to itself, and then it is positive semi-definite. It means that no matter what value of what vector V you plug into this matrix, this inequality will hold. Furthermore, this is equivalent to saying that all the eigenvalues are positive. Okay, and so the proof of this result, it can be found in the ebook, but basically it just tells you that you will not get negative eigenvalues. So to conclude, what we have relearned in this lecture, we have gone through a lot of detailed discussions of this joint Gaussian PDF. The joint Gaussian PDF takes this form, and the shape and also the orientation is fundamentally driven by this covariance matrix sigma. The center of the Gaussian, of course, is given by this mu, but usually that one is a lot easier to understand. The shape and also the orientation given by this sigma is determined by the eigen decomposition. So you run the eigen on sigma, then you will obtain this u and lambda. This u will tell you the orientation, and this lambda will tell you the radius of the major axis and also the minor axis. And we've gone through some examples of illustrating how different sigmas will give you different shapes of the Gaussians. So this is the end of today's lecture. I hope you've learned something, something very, very useful in practice. The best way to learn about these is really to sit down in front of a computer and try typing in your program. In this way, you will be able to see how things will look like on a computer, and then you can draw two-dimensional Gaussians, and then you can analyze them. So I will encourage you to do this exercise. If you have any question, please let me know. I will be very happy to help you. Thank you very much. I hope to see you next time.